Let's fix this. All right, so I gave a talk on Monday, and it looked like most people were here already, so this is going to be different. This is more technical and sort of a development update, more similar to Sebastian's than Martin's. So VOLK has a website. You can visit that, libvolk.org. I don't actually get paid to work on VOLK during my time at NRL. There was a time where that was true. Right now, it's all sort of spare time. So let's get into this. So here's my overview of VOLK. So for GNU Radio purposes, we have some modules here where we're developing some kind of signal processing algorithm, and we need it to run faster. So we have someone trying to mess with an antenna, so they want stuff to run faster. So you come over here, and we have these CPUs that have these special instruction sets that we can take advantage of to run code faster than the compiler will build for us with just generic C. I should also say it doesn't have to be instruction set specific. There are other optimizations that you can put in there. I'll show an example of one of those in a quick minute. So we have these header files where each file has the name of some operation that's happening. This is a dot product, you have multiplies, and inside each header there's just a bunch of different implementations for different CPUs or optimization types. Then the VOLK build system generates these machine files, and those get compiled into libvolk.so, and then your GR outage-free module or whatever can take advantage of that and be faster. Since we're at GNU Radio conference, people might not care about this, but GNU Radio is the original user of VOLK, but it's sort of its own project now. One of the questions that I get pretty often is, who else uses VOLK? I don't know. There are other users of it, and I don't know how many there are because this is open source software. People don't have to necessarily come to me to say, like, I want to use this. But I did look on GitHub. They sort of track activity for you. So the main repository lives on GitHub, so you can see how many people are cloning it every day and how many people are coming to look at the GitHub page every day. So this is sort of the graph of, I guess, the month or so, or yeah, about a week, 2 weeks. So here's individual cloners and then total clones per day. It's individual cloners is about 100. The interesting thing here is I looked at GNU Radio's GitHub page, and it's about 50. Yeah. Yeah, so if you do a submodule update, that definitely clones. If you do a submodule pull, I think it's just a pull.
Does, but here the radio numbers half that, right?
Yeah, so it's somewhat surprising. I would expect VOLK to have maybe slightly more, but the fact that it's double is surprising. That said, people can clone GNU Radio from our website. I don't know if there's that many people doing it. Could be. Who knows? It's just sort of an interesting graph there. Let's see. So the year in commits. So we've had 6 releases this year. That seems high. When I was preparing this presentation, I originally thought I was going to come in and say VOLK has reached a certain level of stability and maturity, and it's sort of new development has sort of slowed down. I'm not sure if that's actually true. So 6 releases, 15 committers. We have several new kernels. Those are polar codes that were introduced last GRCon. A surprising one is, it's actually a FC divide. A surprising one was the complex divide. So let's see here. Where did it go? Here are the committers. So same command that Sebastian ran. There's a handful of people doing stuff, which is really great. A lot of the commits were sort of build related, so people getting it to work on Windows. We had some help from Debian maintainers trying to get reproducible builds. All good stuff. One of the surprising things I want to show here is, this will be sort of a recurring theme, is this still sort of necessary? So the 32 FC divide was added. When people were talking about that on the mailing list, I thought that's a little silly. A simple division at this point in time is not really going to do that well for you. Well, as it turns out, great. It does really well. So here's VOLK profiler running. I was hoping that I would run into some bug with VOLK profiler during the presentation, and then I would, because it's a presentation, so running code is obviously going to fail. It didn't. Great. Anyway, here's the graph of essentially this output. This complex divide, just doing it in VOLK with SSE3 and AVX, you get a huge win. Who knew? So that was new this year. Let's see. Go back to here. So real quick, I'll do a sort of overview of SIMD, where I kind of see things being right now. So if you're not familiar with SIMD, it's single instruction, multiple data. It generally looks like this. So you have 4 elements, and you do some operation on them, and then that goes into 4 other elements. And I said 4. It's really whatever your architecture supports. They have different vector lengths. So sort of similar, state of the art. Where are we? So someone mentioned doing fixed point math earlier. And we had the Neon ARMv8 talk yesterday. So I was curious, is doing fixed point math still on general purpose processors still a win? And I think I'm taking away the answer is no. Here's why. So I took the multiply instruction. Here's a AVX2 multiply 16, so multiply shorts. Here's multiply integer, and here's multiply floats, single precision floats. The throughput and latencies are the same for AVX2. Now you say, all right, ARM is a little different, and ARMv7, I definitely remember looking at the instruction TRM, and sure enough, the fixed point or integer math was faster. On GRCon16, it's not. So I think the takeaway here is that on general purpose processors, there's no reason to not do, well, there's no computational reason to not do just floating points. The exception might be if you care about dynamic range a whole lot. On a quick note on Neon, so they have these double word and quad word registers. So the quad word register would be you have 4 elements. Double word is you have 2 elements. Again, with ARMv7, the instruction timing for using a quad word versus a double word register, with a quad word register would take twice as long, which essentially meant that it was microcoded in to use the double word instruction. On GRCon16, that's no longer true. You actually win by doing the quad word register. It's no longer twice as slow, or half the speed. So that's sort of where I see SIMD right now. Might as well use floats in GNU Radio and use the biggest vectors we can. So again, one of the questions that I get often is what's next? So that's definitely going to be user contributed code. So if you have code that's not running that fast, then use VOLK and try to speed something up. So one of the things that we started last GRCon that I thought would be useful, I don't think anyone has used it yet, and it's not in a super stable state right now, is this internal library of sort of intrinsic functions. And I'll walk through that on my code walkthrough on Friday. So if you're interested in using VOLK or learning how to use it, I'll go through pretty detailed on Friday. Another thing is using interns. So VOLK is sort of a prime ground for, like, if you are developing some applications using GNU Radio and you need them to run faster, or you want them to run faster, putting interns onto VOLK is sort of a great way of getting them to do something and getting them to learn. And all the problems that you might solve with VOLK are fairly well contained. So the problems, like the problem is very simple, and you can just send them off and give them a giant TRM and some function name and have them go at it. That's a lot of how VOLK has gotten to where it is right now. So definitely do that. Another question I get a lot, and we heard it Monday, was what about GPUs? So I just want you to address this right off the bat. GPUs take a long time to get to. Will that be true in the future? I don't know. We might have other architectures, so like HSA from AMD might be coming in. We might have GPUs that are no longer using PCI buses, and we'll want to take advantage of that in the future. Who knows? And that'll, again, mostly be driven by user needs and ability to do it. Another is coprocessors. I've tried with some coprocessors that are like traditional DSP type chips, and they basically suffered from the same problem that GPUs suffered from, at least using VOLK to access the coprocessors. So also just keeping up with processors is going to be next, waiting for my pull request for ARMv8. And I occasionally get some question about PowerPC, and this is mostly from people trying to send up PowerPCs in space because they're rad hard. I think we removed a bunch of AltiVec code from GNU Radio because I had no way to actually QA it and maintain it. So that probably won't exist in VOLK in the future, only because I have no way of actually verifying that it still works. And yeah. And the other question is, when do we stop writing this kind of code? And that sort of relates to what the panel discussion earlier. If we have these crazy system architectures in the future where we don't even know where the code will run, how do we write optimized code for it? Well, from where we stand right now, I don't necessarily think that's an issue. So I would like to show a quick amount of code right here. So this is GNU Radio version 0.9. It's a long time ago. And it's actually kind of hard to get this code, but you can download it. Here's a complex dot product. It's actually SSE, and they copied in the generic version. So this code has existed for a long time. Here's a to-do note. They can prefetch. They would like to do prefetch and better scheduling. Real quick, I would like to show you GNU Radio version 3.7.10.1. Does this look familiar? Yeah. So another question that I got from Monday was, what about making all the functions inline? As long as we still have to-do notes like this around, I think inlining functions is basically not an issue. Yeah. So that's all I have. Are there any questions? Yes, several.
All right, yeah, if you guys could come up, that'd be good. Out of curiosity, what 0.9.2, is that 2000?
It was just
2001?
0.9.
2001, 2002?
I think it was 2001. Is that
2001?
right? Does that sound right?
Raj?
Thank you, Raj.
Yeah, is there a place online where all the kernels are profiled in some kind of standard test rig? At least all the kernels that you can run, let's say all the x86s that, is there a nice standardized test bed where I can go and look at, if I have this architecture and I have AVX1 and 2, what can I expect the performance to be?
Yeah, so there's no, we don't keep any kind of profile that's automatically updated. That would be kind of an interesting thing to do. If someone wants to contribute that kind of thing, that would be great. One of the things that I've gotten some interest in is doing continuous integration. So there's a appver YAML file in there now because someone wanted to have a continuous integration on Windows. I don't follow that, and I don't know if that could generate some profilers automatically.
What about stats.gnuradio.org?
Yeah,
Were you actually actively trying to hide that?
I was sort of trying to forget about it. Thanks, Tom. Yeah, so this exists. I don't know if anyone is still updating results here. That's why I wasn't going to mention it.
It's automated. I believe it's automated.
It was automated from PyBombs at one point. I don't think it is now.
Oh.
Yeah.
I had one question. So you made a comment about fixed point acceleration,
Yeah.
and so that could come from two sources, really, just the differences in the execution unit, or the fact that you're basically trying to shove more things into your long registers. It's kind of hard for me to believe that, at least for some things where there's an 8-bit command, that wouldn't be faster than a 32-bit command if you're fully utilizing the register.
Is that just because you're moving less bits around your buses?
Well, no, in every vector operation, you're just doing 4 times as much as a float if
Oh.
you're. So I just wondered whether your comment covered that case as well.
So I would have to go back and look at, so this is really taken from, here, I'll show you. So, where are we? Here we go. Yeah, so here's the website where you can look up what the timings are. And so the vector lengths are all the same. So I don't know, well, actually, that's not true. For the EPI-16, you might be moving around twice as much data. So for the
Vector
shorts,
lengths,
you might be doing better, but for the 32-bit integers, I don't think you are.
I totally believe that might be true, yeah.
You have any other questions for Nathan? Nope. All right. Let's give him a round of applause. Thank you, Nathan.